early on a summer morning, and Sandy wanted to get in a little fishing before breakfast. He wanted Bud to bring the artificial light or sunlight. What is light? Just how does it affect us? The light from the rising sun is always a source of inspiration and wonder. Throughout the ages, men have associated light with truth and knowledge, darkness with ignorance and evil. And although even today there are questions about what light is, we do know a great deal about how it behaves. This is the science of optics. We know that light is a form of radiant energy traveling through space at the amazing speed of about 186,000 miles per second and capable of producing the sensation of sight. You are using your sight to see that Sandy has found a good spot to cast. Like those ripples in the water, light radiates from its source in a pattern of expanding waves. Light waves radiate in all directions in straight lines, sometimes called rays. However, it is easier to study light in terms of a single ray. Just as a stone skips off water, light rays bounce. This is called reflection. A smooth surface gives regular reflection, but a rough surface reflects the light in many directions. We call this irregular or diffuse reflection. It is the light reflected diffusely from rocks, trees, and such objects that enables us to see these things. Reflection, Bud thought. That's what they were talking about after their fishing yesterday. Sandy and Bud like to have simple versions of demonstrations they've seen in the science lab at school. The bright sun pouring in through a tiny hole in the tent provided a ray of light, and with a few simple gadgets, they could see how light behaves. A shiny piece of metal made a mirror. What happens when light bounces off a reflecting surface like this? They could see the angle of the reflected beam as the mirror was rotated. Sandy showed Bud the relation between the incoming light and the reflected. Regardless of the size of the angle, the law of reflection is the same. The angle of incidence, that is, the angle at which a ray strikes the surface, is equal to the angle of reflection, the angle at which it leaves. This principle is true not only for flat or plane mirrors, but also in a slightly different way with curved mirrors. At different parts of the curve, the rays are reflected at different angles. A concave mirror converges the ray, while a convex mirror spreads or diverges them. Sandy said he could always remember concave by thinking of a sort of a cave, hollow. Convex is the other way. These principles are used in the trick mirrors you often see in amusement parks. Bud makes a more practical use of a curved mirror when following his hobby of photography. The interior surface of this reflector is curved so that the light is directed toward the picture-taking area. So that's what happens when light is reflected from things. Now what happens when light goes through things? Well, it appears to go right through this glass. Actually, however, while light is passing through glass, it slows down to about 2/3 of its normal speed. In the air again, it resumes. When the rays enter the glass at an angle, this slowing down and speeding up causes refraction. Rays that enter first slow down first, causing the beam to bend. They also leave the glass first and speed up first, causing the beam to bend back parallel to its original direction, but offset or shifted. When Sandy handed Bud a glass prism, he could see how the sloping sides changed the direction of the beam. Back in the boat, Bud could see refraction as he dipped an oar. Because light coming from the underwater parts of the oar is speeded up when it comes out, the rays are bent, and so make the oar appear to be bent. Right now, Sandy isn't concerned with refraction. He's got a bite. But Bud is going to use refraction in the camera lens to get a picture of this. Just as he was telling Sandy yesterday, light is refracted in a lens. A lens is really a sort of prism with curved sides. The light rays are refracted or bent toward the thick part of the lens. The point at which the rays meet is called the focal point, and the plane in which all such points lie is called the focal plane. A camera is simply a light-tight box with a lens. At the focal plane of that lens is a sheet of light-sensitive film. This is how an image is formed by light rays. Light reflected from, say, the nose of the fish enters the lens where it is refracted and brought into focus on the film. Light from this point on the nose focuses at this point on the film. The same thing happens to the light from a point on the tail and from every other point in the picture area. So it all adds up to an image on the film, which becomes a permanent photographic souvenir and printed in Bud's darkroom. Sandy didn't think the little print did the fish justice, so Bud offered to make him a big one with his enlarger. He explained that the enlarger uses a lens and the same principles of refraction as the camera, except in reverse. Light is projected through the negative and focuses a larger size image on the easel. But Sandy could not see his picture at all if it were not for another marvelous optical instrument, the human eye. Like a camera, the eye has a lens which focuses light rays on the retina. When a person's eyes are unable to focus clearly, his defect is corrected by eyeglasses, lenses which refract the light so the image is focused sharply. A pair of binoculars can be added to the eye's optical system to enable us to see distant objects clearly. A microscope does the same thing for small objects, while the observatory telescope enables us to look into outer space. Did you ever stop to think about the many uses we make of light, the everyday things around us, and the less obvious applications? Motion pictures, television, the electric eye? You can demonstrate for yourself, just as Bud and Sandy did in their own way, many things about reflection from plane and curved mirrors, and about refraction, and what that means to lenses and to the whole science of optics. And there's a great deal more you will find interesting about the nature of light. For instance, do you know the parts played in this scene by the reflection and refraction of light?
Right now, at this very moment, as you watch these light rays striking the magnified eye, similar tiny beams of light are entering your own eyes. And it's by our eyes that we are able to gain a great part of our knowledge. Now, just how do light rays act to form a clear picture within the eye? First, let us realize that light rays reflected from any object radiate in all directions, and that as an object moves farther away from us, the angle between the rays that enter our eyes grows smaller and smaller. And finally, when the object has reached a distance of 15 feet or more, the rays entering our eyes are practically parallel. Now, nature has provided that parallel rays shall produce a sharp image upon the retina without any effort, and, as one may say, with the eye in a state of complete relaxation. But if a distant object approaches the eye, the angle between entering rays again grows larger. This increasing angle changes the direction of the light rays as they pass through the lens, so that the sharp image falls behind the retina. As a result, the image upon the retina tends to become blurred. This blurring causes a response or reflex within our brain, which brings about harmonious internal adjustments of all parts of the eye. This adjustment is called accommodation. Accommodation restores the sharply focused image with marvelous speed and accuracy. This is all the more remarkable because the distance between lens and retina is fixed, and the lens itself must change its shape. Now compare this with the focal adjustment of a camera. Here the lens remains unchanged, but the film itself is moved until it reaches a sharp focal image. It is also necessary that both our eyes be fixed upon the same point in order that we may see an object clearly. Thus, as an object approaches us from a distance, our eyeballs turn accordingly. This movement is called the convergence of visual axes. This action is shown here as the object approaches and recedes. Here, in addition, we see the lenses accommodating their optical shape under the combined influence of blurred image and eyeball movement. It is well for us to know that our eyes are one of our greatest gifts of nature and are indeed worthy of our constant care and protection.
Electrons? Moons speeding around a giant planet made of gas? Planets orbiting a distant star? Satellites? This light is an idea that promises new understanding simply by delivering fresh perspectives and new perceptions. What do we know? What do we really know? What do we know to be true? We perceive light, we see it, but what we see and what it means are not the same. Without context, detail means nothing. Oh, there are so many factors at play here. What wavelengths of light can we see? How well can our brains take what we see and turn it into something we understand? And also, how do we compare ourselves to the thing we're observing? What tools do we use to help us capture information? How do we turn light into data, data into pixels, pixels into meaning? Start with a planet.
Europa. Jupiter. Enceladus. Io. Iapis. Mimas. Ganymede. Neptune. Triton. Venus. Tethys. Uranus. Callisto.
For example, Earth. And as long as we're at it, let's tip the Earth to spin properly on its axis. Now, recall our original points of light, our idea. These are satellites in orbit. Satellites collect data as the Earth rotates beneath them. Think of satellites as paintbrushes working in reverse. Instead of painting planets with light, satellites collect light reflected from planets below. With enough data, we can paint a world. Data that make this image come from instruments on two NASA satellites called Aqua and Terra. These instruments see the Earth in what we might regard as natural color. They can also see certain events as they happen. There, splattered like white paint on a blue canvas, something important. Hurricane Katrina. These satellites are only two of many that can see hurricanes. But to look inside, we need something specially built for the job. Here we go. The stripes you see building up come from a unique spacecraft called TRIM. Among the many remarkable things TRIM can do, it can look inside hurricanes like nothing else in the world. See for yourself. TRIM sees the actual body of the beast in 3 dimensions. Orange and red zones indicate higher rainfall rates. Cloud spires, called hot towers, drive the storm's greedy grab for energy. Removing the clouds, a separate instrument on the Aqua satellite measures ocean temperature. Temperatures matter. Warm water is the gasoline that powers hurricane engines. This thermal footprint shows fuel in the tank, vital information for forecasters and scientists. The Earth changes. It breathes. And it surprises. Though we live on a planet largely covered by water, we often forget that huge tracts are frozen solid. Let's change the perspective. Ice covers much of the world. The eternally frozen parts are called the cryosphere. It's the planet's thermostat and a hydrological warehouse. And in terms of a changing climate, it's the canary in a coal mine. You may live your whole life and never visit these places, but these places will affect your life nonetheless. You know this place. We haven't been here in a while, but that's about to change. The moon, Earth's closest neighbor, is little more than a beautiful stranger across an airless room. There are mysteries here, and answers, and, like love perhaps, destiny. These are the 6 lunar neighborhoods astronauts visited decades ago. Pack your bags. We're going back soon. Back on Earth, day and night change like moons, with points of light pricking the darkness like vaguely remembered dreams. City lights shine into space at night, like ancient campfires, like candles of civilization. No other place beyond the Earth shows signs of life like this, or shows signs of life at all. But we're looking. Before we can find life elsewhere, we need to be good at reading its signs at home first. And on Earth, life is everywhere. This is the living Earth, the biosphere. Phytoplankton bloom in vast oceanic fields. Land plants pulse rhythmically with seasonal growth. Together, these sound the global heartbeat, the pulse of life powered by the sun. The sun. All energy on Earth comes from the sun. The car you rode in this morning, the unabashed tomatoes and perfumed basil you coax from your garden each summer, the 2 bars out of 5 on your cell phone. They're all quantities of energy. And that means they're all connected to the sun. If you live on Earth, this is the nightlight that matters most. The moon, the earth, the sun. Celestial spheres we see and feel every day. But in our solar neighborhood, there are other places too. Fabulous places, mysterious places. As a tourist destination, Mars has an impressive brochure. The longest, deepest canyon in the solar system. A crater so vast that its edge stretches over the horizon. A volcano so high, its peak climbs above most of the Martian atmosphere. Nothing like these places exists on Earth. Nothing. This is Mars seen differently. You're looking at an elevation map made with an orbiting laser. Red and white areas reach high above the average. Blues and purples show lowlands. If Mars were covered in oceans, the northern hemisphere would be underwater. Imagine the first human footprints left on the shore. What is the world we create in our minds? We create depending on what we want to see. At first, it was enough just to walk, to run, to get wet in the rain, to simply touch the forces of nature. But once in motion, imagination. Then space, perspective. We see what we set out to find. We see what we choose to see. There are often surprises. This is from a NASA mission called WMAP. If the whole universe were a person, this would be its first baby picture. There are no stars here, no galaxies, certainly no planets. But there is energy. The rest came soon enough, once the new kid could collect herself. This is the universe we see today. It's a lively place. That's a gamma-ray burst, spotted by NASA's SWIFT satellite. These cosmic blasts have long puzzled scientists. They may be stars collapsing in upon themselves, or two densely packed remnants of stars merging together. But in either case, scientists believe they herald the births of black holes. They're the most powerful explosions in the universe after the Big Bang, and they seem to happen all the time, as often as once a day. Satellites like WMAP and SWIFT are rapidly coloring our perceptions about our place in the universe. What we know is a function of what we think to ask, what we challenge ourselves to see. We look outwards as much as we look inwards. For if there is any certainty in the journey of knowledge, it's that travel in any direction can lead to the same destination. We see only what we look for. And in space and on Earth, we seek the wisdom to ask the right questions.